Well, good morning, good afternoon, or good evening, depending on when and where you might be listening to me from. My name is Joe Lamb, and this is the first in the new series of AP Chemistry videos that I am super excited to bring you today. Now, these videos are primarily designed for kids that have taken my courses. That is, they've had 2 years of prior chemistry. And so what that means is that I'm probably not going to dive into the details of the fundamental aspects of chemistry. I have other videos that certainly cover those. But what we're really going to focus on today is the upper level chemistry material that is going to be required to be successful on the AP chemistry exam. And today we are going to introduce the first part of Unit 1, which is going to include things like molar conversions, average atomic mass, and mass spectroscopy. Now, many of these things we have talked about previously. You definitely want to keep in mind that the question level at which you're going to be asked to respond is going to be much higher than what you have done previously. So let's dive into some of these basic concepts and go from there. So hopefully by the end of this video, you will be able to perform basic molar conversions between atoms, grams, and moles using molar mass and Avogadro's number. You should also be able to interpret mass spectroscopy graphs and identify individual isotopes, including atomic and mass numbers. Calculate the average atomic mass from a mass spectroscopy graph or data, and identify elements based on mass spectroscopy graphs. Let's go ahead and get started. So very obviously, we've worked with this quite a bit in previous classes. We can't count particles in working with the lab. They're too small for us to be able to individually count. So we have to be able to do some conversions into these things called moles, and moles allow us to convert between one unit and another. It's a counting number. For example, like a dozen. If you have a dozen eggs, a dozen iPhones, it's still the same number. And then we can do conversions based off of stoichiometric ratios and things like that. So we do need to keep in mind the two major numbers that we utilize when we convert, and that is Avogadro's number, which tells you that there are 6.022 times 10 to the 23rd atoms, molecules, or particles per mole, and use molar masses, which we can find on the periodic table. The molar masses are ways that we convert between grams and moles. So if you take a look at the image here on the right, this is the mole wheel, and this mole wheel really helps to break down how we fundamentally convert between grams, moles, and atoms. In order to convert atoms, molecules, and particles on the bottom to moles on the left or right side, we have to use Avogadro's number. If we want to go from atoms, molecules, or particles to grams, we cannot do that with a direct conversion. We need to convert that to moles first and then convert moles to grams. Remember, when we calculate molar masses for compounds, we need to add up all of the individual atoms that make up that compound, keeping in mind subscripts for balanced chemicals and things like that. Also keep in mind that we can determine the number of atoms or grams of a specific element within a compound by looking at the ratio of the compound to the subscripts within the compound. So for example, if I'm given CO2 and I want to know how many grams of oxygen there are in so many CO2 atoms or molecules, I would have to convert between moles of CO2 and moles of oxygen, keeping in mind that there are 2 moles of oxygen for every 1 mole of carbon dioxide. You'll see what I mean when we look at the next practice problem. So the question here is asking to determine the number of atoms of carbon that are found in 9.23 grams of C2H4. So we need to think about where we are going to start. We're going to start with the number that is given, which is 9.23 grams of C2H4. Using the molar mass that I would find on the periodic table, I am then going to convert my grams into moles. If I go back and look at the mole wheel, that's the only thing I can knowingly convert grams into, at least at this point in time, is moles. So I'm going to convert my grams to moles of C2H4. Now I'm going to do what I talked about previously and find the individual moles of carbon for however many moles of C2H4. So for every 1 mole of C2H4, because the subscript of carbon is 2, I can say that there are 2 moles of carbon for every 1 mole of C2H4. And then based on the information of Avogadro's number, which is 1 mole is equal to 6.022 times 10 to the 23rd atoms of carbon, I can then determine the number of atoms of carbon that is found in that. So the stoichiometry problems get a little bit more complex as we go through and think about the next level of chemistry that we'll be taking. But the real key difference here between this and what you've probably done previously is that third step where we have 1 mole of C2H4 to 2 moles of carbon. You can take the individual moles of an element within a sample or within a compound and use the mole ratio in order to be able to figure that out, basically by using the subscript, the fact that there are 2 carbons in 1 mole of C2H4. All right? So let's move on to the next part. Now, one thing we need to think about is average atomic mass. When you look at the numbers on the periodic table, so for example, carbon is 12.01, hydrogen is 1.01, nitrogen is 14.01. That molar mass is an average atomic mass, that it is a weighted average. It is the weighted average of the masses of all those natural isotopes multiplied by their abundance. So how do we figure this out? Is we multiply the mass of each isotope by the abundance percentage and add the resulting products. Based on that information, we can then figure out what the average atomic mass is. Now again, all this information is found on the periodic table. But in a sample, you may have a little bit of leeway one way or the other based on the elemental composition of the sample itself. Let's look at a sample calculation. So what is the average atomic mass of silicon given the following abundance information of the isotopes of silicon? We have a mass number of 28 with an abundance of 92.21%, silicon 29 with an abundance of 4.7%, and silicon 30 with an abundance of 3.09%. Well, remember, when we go through to calculate these, we're going to take the mass number, 28, and we're going to multiply that by the abundance. Remember that when we multiply percentages, we have to get them into their decimal form. So we're going to do that for all three of these. And then we're going to add them together when we are done. And when we add them all together, we get 28.11. And if you think about that number, it makes sense because the abundance of Si28 is significantly greater than that of 29 and 30. So you would expect that the average atomic mass would be somewhere close to 28, or at least closer to 28 than it would be to 29 or 30. Being able to mentally figure out and think about these things is going to be very, very helpful when you analyze mass spectroscopy graphs. In addition to that, this also makes sense because our value, 28.11, is in between our lowest mass number and our highest mass number. If you get an average atomic mass that is significantly lower or higher, I should just say lower or higher in general, than the lowest or highest mass number, you may want to go through and redo your calculations. But all of this is simple algebra. So mass spectroscopy is actually a very useful tool. It uses vaporized ions and a strong magnet to separate ions based on their size to charge ratio. So essentially, we give all of these ions a similar charge. And if we notice here, things that have a smaller mass but a similar charge, so for example, if I look on the right-hand side here, we have isotopes with a mass of 46, 45, and 44. Those with a smaller mass and yet a similar charge are going to curve off of that path with that magnet earlier than ones with higher masses. Think of like a magnet. A magnet pulling on something is going to attract something that has a smaller mass more than it's going to attract something that has a greater mass. And so as a result, there's a detector at there's a detector at the end of the mass spectroscopy instrument that detects the number of hits and calculates a percentage of the isotope based upon the sample. So we can do this in lab. We can actually determine the percentage of each individual isotope and graph that. And then based on that information, we can solve a variety of different problems based on average atomic mass. So what we end up getting, like I said here, is a nice graph that can be analyzed for average atomic mass, or we can use to determine what element is present in there. Now, this gets a bit more complicated when we start looking at compounds. In this class, we're not going to be looking at compounds. We're going to be looking at individual elements. But do keep in mind later on, maybe in a analytical chemistry class, that you could use this to determine compound composition as well. Look closely not only for the mass, because those are not the atomic numbers, but the relative abundance as well. So when you look at the graph here and you see 10 and 11, that is not telling me that those represent neon or sodium. Those are telling me the masses. Remember that the mass number is the atomic number plus the number of neutrons that are present in the sample. So we would have to go through and average those out to be able to figure out what element that is. Or again, a very useful tool is to be able to kind of ballpark it just based on the visualization that you see there. So if I'm taking a look at the graph here on the right, I want to know which element is present in this particular sample. So if I take a look here, I notice that I have a significant mass that is close to 80. I've got quite a bit at 78, 77, 76, 74. So what I want to do here is I actually want to go to my periodic table. I'm going to get one out real quick. And so now I'm looking at my periodic table and I'm looking for my average atomic masses that are somewhere between 74 and 80. And what I find is really three elements that this could possibly be. This could either be arsenic, 33 on the periodic table, which has an average atomic mass of 74.92. Well, if I look at that graph here, it's not going to be arsenic because if I look at those weighted averages, most of the abundance is with a mass number of 80, and 78. So I know it's going to be significantly higher than 74. So I have bromine, I'm going jumping ahead of selenium here, which is 79.90. And while, yeah, most of the mass of these isotopes is 80, there's some at 74, some at 76, some at 77, some at 78. I don't think it's going to be 79.9. So my best estimate here is probably going to be selenium, because the average atomic mass looks to be around 79 just by looking at those masses. You've got a little bit more than 50% at 80. The rest of those combined are going to be around 50%. So it's going to be, somewhere around 79, maybe a little bit less than that. Selenium has a molar mass of 78.87 grams per mole, and the next element, bromine, has a mass of 79.9, which would be too high. And below selenium is arsenic with a molar mass of 74.92, which is too low. So again, it's important to be able to look and ballpark these figures, to be able to do these relatively quickly, because you may not necessarily have time on an exam to be able to go through and do the full calculations for this. Determine the number of protons and neutrons from the most abundant isotope. Well, the most abundant isotope here is selenium 80. And so if I look at my periodic table, selenium has an atomic number of 34. And so as a result, it has to have 46 neutrons to equal the mass number of 80. Remember that the mass number is equal to the number of protons, which is the atomic number found on the periodic table, with the number of neutrons. So 80 minus 34 is going to give me 46. So being able to go through and analyze these relatively quickly, taking your time with your stoichiometric calculations, and knowing how to calculate average atomic mass, very important for the first part of this unit. Hopefully you've got all the student learning objectives for this particular video. Again, I really appreciate your time. More videos will be coming out here soon as I get a chance to publish them. I hope you all have a great day. We will see you soon, and we'll talk to you very, very soon. Bye.